Out there in the vast darkness of space, something is calling to us, not with words, not with images, but with bursts of energy so intense they cross billions of light years just to whisper in our telescopes. These aren't random cosmic noises, they're deliberate, mysterious, and utterly baffling. Scientists have catalogued 40 of these strange signals, each one a puzzle waiting to be solved. Some last just milliseconds, vanishing before we can fully grasp them. Others repeat in patterns that defy explanation, like a distant drummer tapping out a code we can't yet understand. What are they? Where do they come from? And most chilling of all, could they be trying to tell us something? Picture this, a signal so powerful it outshines entire galaxies for the briefest moment. That's exactly what astronomers witnessed when they first detected a fast radio burst, or FRB. These cosmic flashes are among the most energetic phenomena in the universe, and yet their origins remain one of astronomy's greatest mysteries. Some theories suggest colliding neutron stars or evaporating black holes. Others dare to ask the question we're all thinking: could these be signatures of advanced civilizations reaching out across the void? The sheer distance these signals travel means they began their journey before Earth even existed. That's how ancient they are, and yet here they are, arriving now, as if the universe timed their delivery just for us. This isn't just about scientific curiosity, it's about what these signals could mean for humanity's place in the cosmos. Every unexplained burst, every repeating pattern, is a clue that challenges our understanding of physics, time, and even life itself. Are we alone, or is the universe far stranger, far more alive than we ever imagined? Over the next minutes, we'll dive deep into the most compelling theories, the cutting-edge research, and the mind-bending possibilities behind these 40 mysterious signals. From the depths of distant galaxies to the frontiers of human imagination, this is a journey into the unknown. And trust me, what we're about to uncover will leave you questioning everything you thought you knew about the cosmos. The story starts now. It was just an ordinary day in the year 2001 when the universe decided to send us a message. Hidden in the static of routine telescope data, a spike of energy appeared, so brief it could have been dismissed as interference, so powerful it rewrote our understanding of the cosmos. Scientists combing through old observations from the Parkes radio telescope in Australia froze when they saw it, a 5-millisecond blip, later named FRB 010724. In that fleeting moment, it unleashed more energy than our sun emits in 80 years. And then, just like that, it was gone. No warning, no explanation, no trace. At first, researchers wondered if it was a glitch, perhaps a satellite passing overhead, or even a microwave in their own facility accidentally leaking interference. But when similar signals began popping up in other telescopes around the world, the truth became undeniable. This was something real, something extraterrestrial in the purest sense, a burst of radio waves from billions of light years away, piercing the darkness like a cosmic flare. The discovery sent shockwaves through astronomy, forcing scientists to confront a humbling reality. After centuries of studying the stars, the universe had just handed us a phenomenon we couldn't explain. Theories erupted like sparks from a fire. Maybe it was the death scream of a neutron star collapsing into a black hole, or the shockwave from two superdense stellar corpses slamming together. Some dared to whisper the possibility that shook the scientific community. What if this wasn't natural at all? The signal's sheer intensity, its perfect frequency sweep, almost seemed engineered. Could something or someone have crafted it? FRB 010724 didn't just defy explanation, it exposed how little we truly know about the universe's hidden symphony. Before this, no one imagined space was filled with such violent, fleeting whispers. Now, every time a telescope points skyward, we're listening not just for answers, but for the next great cosmic question. Because if one thing's certain, it's this: the universe loves a mystery, and it's just getting started. Just when scientists thought they were starting to understand these cosmic anomalies, the universe threw them a curveball that changed everything. FRB 121102 didn't just flash and vanish like its predecessors, it came back, again and again. This wasn't a cosmic one-hit wonder. It was a persistent signal, broadcasting across 3 billion light-years of space like a radio station that never signed off. The discovery sent shockwaves through astronomy, shattering the assumption that all fast radio bursts were singular events. Here was proof that whatever created these signals could do so repeatedly, with precision that defied natural explanations. Tracking its origin led researchers to a tiny, unassuming dwarf galaxy, a cosmic backwater where stars formed at a frantic pace. This unlikely setting only deepened the puzzle. Why would such a faint, small galaxy host something capable of generating these colossal energy bursts? The leading theory points to magnetars, neutron stars with magnetic fields so intense they could strip the electrons from atoms 1,000 kilometers away. Imagine a spinning, city-sized magnet with the mass of a sun, twisting space-time itself as it rotates. When its crust fractures under unimaginable stress, it might unleash these radio shockwaves like cosmic earthquakes. But even this dramatic explanation has holes. No known magnetar pulses with the regularity or power of FRB 121102. Then there's the pattern, or lack thereof. Unlike the steady tick of a pulsar, these repeats seemed erratic, sometimes clustering together, other times falling silent for months. It's this unpredictability that keeps the door open to more. Speculative ideas: could this be a beacon deliberately designed to catch our attention? The energy required aligns with theoretical megastructures proposed by advanced civilizations. Imagine a power source harnessing the energy of an entire star, focused into laser-like bursts. While extraterrestrial origins remain a long shot, the mere possibility forces us to confront an electrifying question. If something out there is engineered, how would we even know? What makes this signal truly extraordinary isn't just its repetition, but what it reveals about the universe's hidden diversity. Before FRB 121102, astronomers assumed all fast radio bursts were created equal, cataclysmic, one-time events. Now we know the cosmos has at least 2 playbooks for these phenomena, maybe more. Every time it reactivates, it's as if the universe is whispering, "You haven't figured me out yet." And with each detection, we're reminded that the greatest discoveries often come from the signals that refuse to be ignored. Fast radio bursts shatter our cosmic expectations the moment we think we understand them. Imagine a single burst packing more punch than 500 million suns, all compressed into a blip shorter than the blink of an eye. That's the staggering reality of FRBs. Since their accidental discovery in 2007, these radio wave tsunamis have rewritten the rules of astrophysics. They don't just challenge our theories, they mock them. Some erupt once and vanish without a trace. Others, like cosmic alarm clocks, fire off repeatedly with no discernible rhythm. And their origins, that's where the mystery turns spine-tingling. Take the most famous repeating burst, FRB 180916. Located in a spiral galaxy surprisingly similar to our Milky Way, it follows a peculiar cycle, active for 4 days, silent for 12, like clockwork. This isn't chaotic stellar debris, it's precision that defies known physics. Magnetars, the universe's most magnetic stars, were the prime suspects until researchers noticed something odd. The energy profiles of certain bursts don't match any known stellar object. They're too clean, too focused, as if channeled through an interstellar amplifier. Then there's the distance problem. Many FRBs originate from galaxies so far away their light has traveled for billions of years before reaching us. That means whatever's producing them existed when the universe was half its current age. Could ancient civilizations have built cosmic lighthouses? It's a fringe idea, but even skeptics admit the math is intriguing. An advanced society harnessing a neutron star's energy could theoretically beam focused radio waves across the cosmos, a deliberate signal spanning eons. Yet the simplest explanation might be the most unsettling. We're hearing the birth cries of entirely new celestial objects. Some theorists propose blitzars, neutron stars so massive they should collapse into black holes but spin fast enough to resist. When they finally implode, their magnetic fields snap like rubber bands, releasing these explosive radio shrieks. Others suggest cosmic strings, hypothetical defects in space-time, vibrating like guitar strings and rippling the fabric of reality itself. Every new detection adds layers to the enigma. In 2020, astronomers caught an FRB inside our own galaxy, finally close enough to study in detail. The culprit, a known magnetar throwing an electromagnetic tantrum. Finally, a smoking gun, but here's the twist. This burst was thousands of times weaker than its extragalactic cousins. So while we've solved one piece, the greater mystery only deepens. Are some FRBs natural and others something else? The universe isn't just sending mixed signals, it's rewriting the rules as we watch. What makes these bursts so captivating isn't just their power or distance. It's what they represent, a frontier where known physics crumbles. Each detection forces us to question whether we're witnessing cosmic accidents or cosmic engineering, until we catch one in the act, until some telescope captures the unthinkable. FRBs will remain the universe's most tantalizing unsolved riddle. And that's exactly what makes them irresistible, because in the hunt for answers, we're not just studying the cosmos, we're deciphering its strangest love letter. Before fast radio bursts became astronomy's hottest mystery, another signal from the stars captured humanity's imagination and never let go. It was August 15, 1977, when Ohio State University's Big Ear radio telescope recorded something extraordinary. A narrowband radio emission, precisely at the frequency hydrogen absorbs and emits energy, the exact wavelength scientists predicted an alien civilization might use to announce itself. For 72 electrifying seconds, the signal blazed 30 times stronger than the background noise before vanishing forever. Astronomer Jerry Amon circled the data printout in red ink, scribbling, "Wow." Beside the string of numbers, that casual exclamation would give this cosmic enigma its name. What made the wow signal so remarkable wasn't just its strength, but its artificial seeming purity. Natural cosmic phenomena usually emit across a range of frequencies, like static across radio stations. This was a laser-like beam concentrated on one specific channel, exactly how an intelligent species might transmit. Even more intriguing, it originated near the Chi Sagittarii star group, where several Sun-like stars host potentially habitable planets. The signal's brief duration suggests it wasn't some celestial explosion. It behaved more like a lighthouse beam sweeping past Earth, giving us one fleeting chance to catch it. For decades, scientists have chased explanations. Some proposed a passing comet emitting hydrogen, except comets don't produce such intense narrowband signals. Others suggested a secret military satellite, though no known human technology matched its profile. The most unsettling possibility remains: we intercepted someone else's transmission. The signal's frequency sits in a quiet radio band, deliberately chosen to avoid cosmic noise. That's not something nature does, but an advanced civilization might. What haunts researchers isn't just the mystery of what caused it, but the realization of how easily we could have missed it. The Big Ear telescope observed that patch of sky for just 72 seconds before moving on. Had the signal arrived moments earlier or later, we'd never have known it existed. That raises an electrifying question: how many similar calls have we overlooked? Modern telescopes like the Allen Telescope Array now constantly scan the stars, hunting for another wow. But here's the twist: with fast radio bursts now dominating the search for cosmic mysteries, could some FRBs actually be artificial signals we're misinterpreting? The WOW signal's legacy isn't just about one unexplained blip on a printout. It's a humbling reminder that the universe might be shouting at us in ways we're only beginning to hear. Every unexplained signal, whether a 72-second whisper from 1977 or a millisecond burst from a billion light-years away, carries the same thrilling possibility. We might not be the only ones listening, and out there in the cosmic dark, someone or something might finally be calling back. Sometimes the universe plays tricks on us, delivering signals so strange, so unnervingly precise, that even scientists momentarily believe they've found proof we're not alone. That's exactly what happened in 1967, when graduate student Jocelyn Bell Burnell noticed an anomaly in her radio telescope data: a pulse. Not random static or cosmic noise, but a steady, unbroken rhythm: beep, 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 spaced exactly 1.337 seconds apart. It was so mechanically perfect that her team jokingly labeled it LGM1, Little Green Men 1. For weeks, they quietly considered the unthinkable. Had they just intercepted an alien beacon? The truth, when it came, was almost as astonishing. Those metronomic pulses weren't from extraterrestrians, but from something no one had ever observed before: a pulsar. A spinning neutron star, the collapsed core of a dead sun, no larger than a city but denser than anything in existence. As it rotates, its magnetic poles sweep beams of radiation across space like a cosmic lighthouse. When those beams intersect Earth, we detect them as pulses. Nature, it turned out, could mimic intelligence with breathtaking precision. This historic mix-up holds profound lessons for today's hunt for cosmic mysteries. If something as mundane, relatively speaking, as a spinning star could masquerade as an alien transmission, what else might we be misinterpreting? Fast radio bursts, with their erratic patterns and mind-bending energy, push this question to its limits. Some FRBs repeat, but never with pulsar-like regularity. Others explode once and vanish, leaving no trace of their origins. The problem isn't just identifying what creates them, it's confronting how little we truly understand about the universe's capacity for generating signals that defy categorization. Pulsars taught us an important truth: the cosmos is full of natural phenomena that look engineered. Magnetars twist spacetime into knots. Quasars blast jets of matter millions of light years long. So why couldn't FRBs be another example of physics performing magic we haven't yet decoded? On the other hand, the LGM1 episode also reminds us not to dismiss possibilities too quickly. What if, buried among the thousands of detected FRBs, there's one that doesn't fit any natural explanation? The challenge is recognizing it without letting hope cloud judgment. This delicate balance between skepticism and wonder fuels modern astronomy. Every unexplained signal carries two stories, one written by the laws of physics and another whispered by our imagination. The pulsar mistake humbled us, yes, but it also expanded our vision. Before 1967, no one dreamed dead stars could tick like clocks. Now, as we confront fast radio bursts, we're forced to ask, what other cosmic surprises are waiting in the data, masquerading as something they're not? The universe loves a good mystery, and sometimes the greatest discoveries begin with a signal we almost didn't take seriously. The discovery of FRB 180916 didn't just add another puzzle piece to the fast radio burst mystery, it flipped the entire board. For the first time, astronomers traced a repeating burst back to its cosmic neighborhood, a star-forming region in a spiral galaxy, a mere 500 million light-years away. That might sound impossibly distant, but in the grand scale of the universe, it's practically next door. This proximity was a game changer. Suddenly, scientists could study an FRB's home turf with unprecedented clarity, and what they found was utterly unexpected, a clockwork rhythm. Every 16.35 days, like celestial clockwork, FRB 180916 springs to life. For 4 days, it fires off bursts, sometimes several an hour, before falling silent for 12. This isn't the erratic stutter of a dying star or the chaotic aftermath of a collision. It's a pattern so precise it hints at orbital mechanics, as if something is moving in a slow, predictable dance. The leading theory, a magnetar locked in a gravitational tango with a massive companion, perhaps a blue supergiant star or a black hole. As the magnetar orbits, its powerful magnetic field might periodically interact with stellar winds or debris, creating bursts like a cosmic lighthouse flickering through fog. But here's where it gets even stranger. If this FRB is tied to an orbiting system, why don't all magnetars in binary pairs produce similar signals? Our own galaxy hosts neutron stars with companions, yet none generate anything remotely like these titanic radio screams. This anomaly has led to wilder possibilities. Maybe the periodicity comes from a precessing magnetar, a spinning neutron star wobbling like a top, its beams sweeping across space at predictable intervals. Or perhaps we're seeing something entirely new, a celestial object that doesn't fit any existing category. What makes FRB 180916 so revolutionary isn't just its regularity, but what it reveals about the diversity of these cosmic signals. Distant one-off bursts might arise from catastrophic events, stellar collisions, or apocalyptic starquakes, but this nearby repeater suggests an entirely different engine, one that operates on cycles rather than chaos. It's as if the universe is showing us two distinct species of FRBs, the fireflies and the fireworks. The implications ripple far beyond astronomy textbooks. If some FRBs follow predictable schedules, we might finally catch one in the act, watching as the burst source flares to life in real time. Telescopes could train their lenses on the exact spot days before the next expected eruption, capturing every wavelength from radio waves to X-rays. That kind of data could crack the code, revealing whether we're witnessing natural astrophysics or something far more extraordinary. For now, FRB 180916 remains a tantalizing clue, a cosmic metronome ticking in the darkness. With every cycle, it whispers the same haunting question. Are we listening closely enough to hear what the universe is really trying to say? The debate over fast radio bursts splits the scientific community into two camps, those who see them as cosmic accidents and those who dare to wonder if there's something more. On one side, the natural explanations paint a violent, chaotic universe. Magnetars take center stage here, neutron stars with magnetic fields so strong they could erase a credit card from halfway to the moon. When these stellar monsters experience starquakes, their crusts snap like brittle rock, releasing energy equivalent to 1 billion atomic bombs. That fits the profile of some FRBs: sudden, explosive, and devastatingly powerful. Then there's the collision theory, two neutron stars spiraling toward each other in a death spiral, merging in a flash of gravitational waves and gamma rays. Such an event could theoretically launch a one-time radio scream across the cosmos. But nature has even wilder cards up its sleeve. Cosmic strings, hypothetical cracks in the fabric of space-time left over from the Big Bang, might vibrate like plucked guitar strings, sending shockwaves through the universe. Or perhaps collapsing black holes, objects so dense they punch holes in reality, emit final radio bursts as they evaporate into nothingness. These ideas push the boundaries of known physics, yet they still fall within the realm of natural phenomena. Then there's the other camp, the one that asks the electrifying question: what if we're not alone? The precision of some repeating bursts, their frequency sweeps, their apparent targeting of specific cosmic neighborhoods, these traits don't automatically scream natural. Advanced civilizations could harness neutron stars as power sources, focusing their energy into narrow beams for communication or propulsion. Imagine a Dyson sphere, a theoretical megastructure enclosing a star channeling energy into interstellar Morse code. The math checks out. The energy required matches what we observe. Even more intriguing, FRBs often cluster around frequencies optimal for piercing interstellar plasma, as if engineered to minimize interference. Here's the twist: the line between natural and artificial might blur. Some signals could be natural phenomena repurposed by intelligence, like a river used as a navigation marker. A Magnetars outburst might be unavoidable astrophysics, but its timing or modulation could carry intentional patterns. This hybrid possibility forces us to rethink our definitions. After all, if an alien civilization built a beacon around a cosmic object, would we even recognize the difference? The search for answers is far from over. Every new FRB detection adds layers to the mystery. Some fit neatly into astrophysical models, others defy them entirely. What's undeniable is this: these signals, whether born from collapsing stars or civilizations we can scarcely imagine, are rewriting the rules of the cosmos. And until we catch one in the act, until we witness the moment of creation, the debate will rage on. Because in the end, the most thrilling possibility isn't just discovering what FRBs are, it's discovering what they reveal about the universe's hidden diversity. Whether natural, artificial, or something in between, they're proof that the cosmos still holds wonders beyond our wildest dreams. For years, astronomers thought they had fast radio bursts figured out, or at least they thought they knew where to look. The repeating signals seem to favor small, scrappy dwarf galaxies, places where stars are born in chaotic bursts and magnetic monsters like Magnetars could thrive. Then along came FRB 190523, shattering that assumption with a single, earth-shaking revelation. This wasn't some cosmic backwater. It came from a massive, mature galaxy, one drowning in metals and old stars. The kind of place where Magnetars should be rare if they exist at all. This discovery threw the FRB playbook out the window. Suddenly, the idea that all bursts come from young, turbulent environments collapsed. The host galaxy of FRB 190523 was ancient by cosmic standards, its star-forming days long behind it. That posed an electrifying question. If Magnetars are typically born from violent supernova in active galaxies, how did this one end up in such a quiet, well-behaved neighborhood? One possibility is that we're seeing a new class of magnetar, one that forms through quieter channels, perhaps when two white dwarfs merge instead of a massive star collapsing. Or maybe Magnetars can survive far longer than we thought, lurking in aging galaxies like relics from a more explosive past. But there's an even more disruptive idea lurking in the data. What if not all FRBs come from magnetars at all? The diversity of host galaxies from sprightly dwarfs to these cosmic retirees suggests multiple roads lead to these brilliant flashes. Some bursts might indeed be magnetar tantrums, while others could stem from entirely different engines. Imagine black holes snacking on neutron stars, or exotic physics playing out in galactic cores we don't yet understand. The universe, it seems, has more than one way to scream into the void. What makes FRB 190523 so pivotal isn't just what it tells us, but what it forces us to unlearn. Before this, the hunt for FRB sources had a comforting narrowness. Now the field has exploded wide open. Every new detection could rewrite the rules all over again, proving that these signals aren't just mysteries. They're mirrors reflecting back how much we still have left to discover. And that's the real message buried in this cosmic static. The universe refuses to be pigeonholed. It delights in variety, in exceptions, in keeping us guessing. And if we're willing to listen, these bursts might just teach us more about the cosmos than we ever thought to ask. Hidden in the rolling hills of British Columbia, an unassuming array of half-cylinders stares skyward Canada's CHIME telescope, a game-changer in the hunt for cosmic whispers. Unlike traditional radio dishes that focus on narrow patches of sky, CHIME 400-meter-long corridor of antennas acts like a wide-angle lens, scanning the entire northern heavens every single day. Since it flickered to life in 2018, this unpretentious instrument has rewritten the rules of FRB detection, catching more bursts in its first year than astronomers had documented in the previous decade combined. What makes CHIME revolutionary isn't just its appetite for discovery, but its knack for revealing hidden details. By capturing hundreds of FRBs, some repeating, some solitary, it's exposed subtle fingerprints in their radio waves, frequency drifts, polarization twists, and energy distributions that act like cosmic barcodes. Each burst carries clues about the environments it traveled through, the magnetic fields it encountered, and the violent processes that birthed it. Before CHIME, scientists were piecing together a puzzle with a handful of fragments. Now they're staring at a flood of data so rich it's reshaping theories weekly. Take the revelation that repeating and non-repeating FRBs might be fundamentally different beasts. CHIME torrent of detections showed that repeaters often have lower frequencies and longer durations, as if they're powered by distinct cosmic engines. Then there's the shocker that some bursts arrive with a side of X-rays, a detail only visible when other telescopes swing into action alongside CHIME alerts. These partnerships have turned the hunt into a global collaboration, with observatories worldwide standing ready to pounce the moment CHIME sounds the alarm. Yet for all its triumphs, CHIME has also deepened the mystery. Its data-revealed bursts clustered in ways that defy randomness, sparking debates about whether we're seeing natural cosmic rhythms or something more deliberate. Even more perplexing, the telescope's sheer volume of detections suggests FRBs might be far more common than anyone imagined, perhaps as frequent as 1,000 lighting up the sky every day. If that's true, why do so few reach our telescopes? The answer might lie in their beaming. Like interstellar laser pointers, most could be shooting harmlessly into empty space, with only a rare few aligned to graze Earth. CHIME's greatest gift isn't just answers, it's the questions we never thought to ask. Every new burst adds another thread to the tapestry, weaving together clues about the universe's most energetic phenomena. And as upgrades boost its sensitivity, this humble Canadian array might soon catch something even more extraordinary, the smoking gun that finally reveals whether these signals are cosmic accidents or cosmic hellos. One thing's certain: the age of guessing is over. We're now in the era of listening, and CHIME is turning up the volume. the year 2020 brought a revelation astronomers had been waiting for, a fast radio burst erupting not from some distant galaxy, but from our own cosmic backyard. On April 28th, multiple telescopes caught an unmistakable signal from a known troublemaker in the Milky Way, Magnetar SGR 1935 plus 2154. This wasn't just any stellar outburst, it matched the profile of an FRB, albeit thousands of times weaker than its extragalactic cousins. Finally, we had proof that magnetars, those ultramagnetic zombies of dead stars, could indeed produce these enigmatic radio screams. What made this detection so groundbreaking wasn't just the confirmation of a long-suspected source. It was the unprecedented detail scientists could capture. Unlike bursts from billions of light years away, this one arrived virtually next door, a mere 30,000 light years from Earth. Telescopes caught not just the radio flash, but accompanying X-rays and gamma rays, painting a full picture of the magnetar's tantrum. The data revealed something startling. The FRB wasn't an isolated event. It came amid a storm of high-energy activity, as if the star's crust had cracked under intense magnetic pressure, unleashing a cascade of radiation across the spectrum. Yet this cosmic Rosetta Stone raised as many questions as it answered. If magnetars create FRBs, why was our homegrown version so feeble compared to those from other galaxies? One theory suggests distance plays tricks. Perhaps extragalactic FRBs beam their energy narrowly, like cosmic lasers, making them appear brighter when aligned with Earth. Alternatively, Milky Way's magnetars might be older, their magnetic fields decayed with time, producing weaker outbursts, but the most tantalizing possibility: that the universe has multiple FRB factories. Magnetars could explain some bursts, while others might stem from rarer, more cataclysmic events, collisions between neutron stars, or black holes birthing new physics in their death throes. The aftermath of FRB 200428 transformed the hunt. Suddenly, astronomers had a template, a known magnetar caught in the act. Teams began scouring archival data, matching past X-ray flares from other magnetars with potential missed FRBs. And they found them, subtle radio blips accompanying stellar quakes, previously dismissed as noise. This hidden population suggests magnetars might generate FRBs more often than we realized. They're just usually too faint to detect across intergalactic distances. But here's the twist that keeps scientists up at night. If magnetars can produce both weak local FRBs and titanic distant ones, what flips the switch between these modes? Is it the star's age, magnetic field strength, or some unseen companion? Or does the environment play a role, like dense nebulas focusing the bursts into tighter beams? Every new observation chips away at these questions, inching us closer to understanding whether FRBs are cosmic accidents, intentional signals, or something stranger still. One thing's certain: the Milky Way's FRB didn't solve the mystery, it turned the key on a whole new chapter. Imagine a civilization so advanced it doesn't just inhabit the cosmos, it reshapes it. That's the provocative idea behind the technosignature hypothesis. The notion that some fast radio bursts might not be natural phenomena at all, but engineered signals. The math, surprisingly, holds up. To transmit an FRB across billions of light years, you'd need a power source dwarfing anything humanity has built, but not one that violates physics. A Dyson swarm, a network of energy harvesting satellites around a star, could theoretically focus a star's output into a narrow radio beam, aim it right, and it would outshine entire galaxies for a millisecond, just like the FRBs we detect. The real puzzle isn't whether it's possible, but why any civilization would do it. One compelling answer lies in propulsion. A laser-like radio burst could push light sails enormous, ultra-thin mirrors attached to interstellar probes. The same beam that propels a spacecraft to relativistic speeds might accidentally sweep past Earth, appearing as an FRB. Alternatively, these bursts could be cosmic lighthouses meant to announce a civilization's presence. The frequency sweep common in FRBs, where the signal starts high and drops lower, mimics the natural dispersion of radio waves traveling through space, almost as if designed to compensate for interstellar interference. Then there's the eerie timing of some repeating bursts. Their irregular yet non-random patterns resemble cryptographic handshakes, the initial exchanges in a communication protocol. SETI researchers have combed FRB data for mathematical constants, prime number sequences, or other hallmarks of artificial encoding. So far, nothing conclusive has emerged. But the absence of evidence isn't evidence of absence. We might simply lack the right decryption key. After all, if an alien message arrived, would we even recognize it as one? Skeptics counter with Occam's razor. The simplest explanation is usually correct. The universe teems with cataclysmic events, magnetar flares, neutron star collisions, that don't require invoking intelligence. Yet even they admit the technosignature hypothesis serves a vital purpose. It forces us to question our assumptions. If we only ever expect natural explanations, we might miss the one signal that isn't. The truth, as often in science, might lie in the middle. Most FRBs likely arise from astrophysical fireworks we're still unraveling. But among thousands of bursts, could there be one that defies all natural explanations? That's the tantalizing edge of the FRB mystery, not just discovering what they are, but remaining open to what they might reveal. Because if the universe has taught us anything, it's that reality is often stranger than fiction. And sometimes the most extraordinary answers begin as the wildest questions. Back in 1961, astronomer Frank Drake scribbled an equation on a chalkboard, a deceptively simple formula that would shape humanity's search for cosmic neighbors. The Drake equation breaks down the overwhelming question, are we alone, into manageable pieces: the rate of star formation, the fraction with planets, the odds of life emerging, and so on, culminating in the big unknown. How many civilizations might be broadcasting their existence right now? For decades, we've plugged in guesses, hoping telescopes might catch a deliberate signal. But fast radio bursts throw a fascinating wrench into this math. If even one FRB out of the 40 we've catalogued isn't natural, if it's a technosignature, then the equation's final variable, the lifetime of communicating civilizations, might need radical revision. Consider the implications. The Milky Way alone could host thousands of advanced societies, each briefly flaring into visibility with FRB-like beacons before fading into silence. Across billions of galaxies, the numbers become staggering. So why haven't we found incontrovertible proof? The Drake equation hints at sobering possibilities. Maybe civilizations are common, but their signals are fleeting, like cosmic fireflies flashing once in darkness. Or perhaps we're like ants trying to decode Wi-Fi, missing patterns in the noise because we lack the right conceptual framework. FRBs challenge us to consider that advanced societies might communicate in ways we can't yet fathom, using physics we haven't discovered. What makes this moment historic is how FRBs are refining the equation's terms in real time. Every new burst detection adjusts our estimates of how often extreme astrophysical events occur, which in turn affects how often we should expect artificial ones. The repeating bursts, with their irregular cadences, suggest some sources are long-lived, upping the odds that at least a few might be engineered. Meanwhile, the sheer diversity of FRB hosts, from dwarf galaxies to metal-rich giants, expands the range of environments where intelligence might arise. Yet the equation also tempers our excitement. Even if FRBs are artificial, the vast gulfs between galaxies mean civilizations might bloom and die without ever contacting each other. A signal crossing billions of light years could be the last gasp of a culture long extinct. Or worse, we might be listening to cosmic graveyards, picking up echoes from civilizations that succumbed to the very technologies we're now developing. The Drake equation was never meant to give answers. It's a mirror reflecting how little we truly know. FRB, in their brilliant ambiguity, are the perfect counterpoint signals that could rewrite the equation's terms or vanish into the static of cosmic coincidence. Each one whispers the same haunting question. In a universe so vast, is it more terrifying to be alone, or to realize we're just one voice in a chorus we're only beginning to hear? Among the dozens of fast radio bursts that have puzzled astronomers, FRB 20201124 stands out like a cosmic fingerprint, utterly unique and brimming with secrets. Detected in November 2020 by China's 500-meter fast telescope, this burst didn't just flash and fade. It carried a peculiar signature in its polarized light, as if twisted by invisible hands during its journey through space. The signal's electromagnetic waves weren't just vibrating randomly, they were spiraling, a phenomenon called Faraday rotation that suggests the burst plowed through an intensely magnetized environment. Picture a lighthouse beam passing through a swirling storm, its light distorted by forces we can't yet see. That's the level of cosmic interference at play here. What makes this distortion so tantalizing is where it happened. FRB 20201124 hails from a spiral galaxy much like our Milky Way, but with a key difference. Its host region crackles with newborn stars. These stellar nurseries are cauldrons of magnetic chaos, where young, volatile magnetars might lurk amid swirling plasma. Some theorists suggest the polarization twists could be the burst punching through a nebula thick with magnetized debris, the remnants of a supernova that birthed the very object now sending these signals. Others propose an even wilder scenario. What if the distortions aren't natural at all? Advanced civilizations might use polarized signals as a form of encryption, encoding data in the spin of radio waves. While that's a long shot, the mere possibility forces us to confront how little we understand about the information capacity of these bursts. Then there's the burst's rhythm or lack thereof. Unlike the metronomic repeats of FRB 180916, this one fired off with erratic intensity, sometimes hurling multiple bursts in an hour before falling silent for weeks. This unpredictability hints at an engine far more chaotic than a simple spinning magnetar. Imagine a cosmic switchboard, flickering on and off as unseen forces, perhaps a black hole's gravitational tides or a companion star's winds, tamper with its power source. The host galaxy's star-forming frenzy only deepens the intrigue. Active stellar birth means frequent stellar death. Could this FRB originate from a magnetar born in a recent supernova, still racked by the aftershocks of its violent creation? What truly sets FRB 20201124 apart is what it reveals about the universe's creativity. No two bursts share identical traits, as if each one is custom-made by its environment. Some sweep frequencies like a cosmic slide whistle, others pulse with almost musical regularity. This one, it's a masterclass in magnetic mystery, proving that even after cataloging 40 of these signals, we've barely scratched the surface. Every new detection isn't just answering questions, it's revealing how much more bizarre the cosmos can get. And that's the real message of FRB 20201124A. The universe doesn't do repeats. It specializes in one-of-a-kind enigmas, each one daring us to listen more closely. For every fast radio burst that screams across the cosmos, there may be 100 others whispering just below our detection threshold. These faint FRBs, weak, fleeting, and frustratingly elusive, are rewriting the rules of what we thought we knew. Unlike their high-energy cousins that outshine galaxies, these quiet signals slip through our telescopes like ghosts, often mistaken for instrumental noise or cosmic static. Yet their discovery hints at something profound. We've been eavesdropping on the universe's loudest conversations while missing the murmurs that might carry the most telling secrets. Take FRB 2019050B, detected by the ultra-sensitive ASCAP array in Australia. This burst was so weak it barely registered, a flicker of radio waves with just 1% the energy of a typical FRB. At first glance, it seemed unremarkable, but when astronomers traced its origin, they found something startling. It came from a galaxy so distant, its light had traveled for nearly 8 billion years. That means this faint burst, barely a whisper to us, was once as powerful as any FRB we've seen, its signal diluted by the mind-bending expansion of the universe. It's like hearing a shout from across a canyon, reduced to a sigh by the time it reaches your ears. This raises a tantalizing possibility. What if the faint FRBs aren't inherently weak at all? Instead, they might be the echoes of cataclysmic events from the universe's youth, stretched and dimmed by time and space. If that's true, their sheer numbers could mean the early cosmos was far more violent than we imagined, crackling with energetic phenomena we've yet to name. But there's another, even stranger explanation. Some of these whispers might not be distant at all. They could be near, by bursts intentionally dialed down. Imagine an advanced civilization using focused radio beams for communication or propulsion. The ones aimed directly at Earth would arrive blisteringly strong, like the FRBs we've catalogued. But signals meant for other targets glancing off our planet by accident would appear faint and scattered. It's a cosmic version of overhearing a conversation not meant for you. The words are there, but barely audible. The hunt for these quiet signals is now a priority. Telescopes like CHIME and FAST are refining their algorithms to catch bursts that would have been dismissed as noise just years ago. Every new detection adds a piece to the puzzle, whether it's a faint repeater with a bizarre cadence or a one-off whisper from a galaxy we've never mapped. Together, they're revealing a hidden layer of cosmic activity, proving that the universe doesn't just shout its mysteries. Sometimes it leans in close and whispers. And those whispers might be the key to understanding everything we've missed. In March 2015, astronomers witnessed something extraordinary, a fast radio burst that didn't just vanish into the cosmic background. FRB 150418 arrived with a flourish, and for 6 days afterward, a faint radio glow lingered at its source, like the dying embers of a celestial fire. This afterglow was unprecedented. For the first time, scientists thought they'd caught an FRB red-handed, leaving behind evidence of its origins. The initial excitement pointed to a neutron star merger, a cataclysmic collision of two ultra-dense stellar corpses. Such an event could theoretically produce both a fleeting radio burst and a sustained afterglow as the wreckage expanded into space. But the universe loves a good plot twist. Later observations revealed a far more complicated story. The fading radio source didn't behave like a merger's aftermath. Instead, it flickered in ways that suggested an active galactic nucleus, a supermassive black hole feeding on surrounding material. Was the afterglow unrelated to the FRB, just a cosmic neighbor stealing the spotlight? Or was there a deeper connection no one had anticipated? The debate raged on, exposing just how treacherous FRB detective work can be. Even when we think we've found a clue, the cosmos reminds us how easily coincidences can masquerade as answers. What makes FRB 150418 so fascinating isn't just the false lead, it's the glimpse it offered into how FRBs might interact with their environments. Some bursts might ignite lingering echoes if they occur in dense nebulas or near powerful magnetic fields. Others, erupting in the void between galaxies, leave no trace at all. This variability suggests an invisible tapestry of conditions shaping each burst's fingerprint. Imagine lightning striking different landscapes, sometimes hitting wet soil and leaving steam, other times hitting dry rock and vanishing without a mark. The hunt for afterglows has since become a high-stakes race. Telescopes now scramble to observe FRB locations within hours or even minutes of detection, hoping to catch these elusive echoes before they fade. A few, like FRB 190523b, have rewarded the effort with faint X-ray counterparts. Others remain stubbornly silent, their secrets locked away the instant the burst ends. This inconsistency fuels the burning question: are we dealing with multiple classes of FRBs, some that leave calling cards and others that operate in stealth? The legacy of FRB 150418 isn't just about a single misleading afterglow. It's a masterclass in cosmic humility, reminding us that even when the universe seems to offer answers, it's often teaching us how much we still have to learn. Every burst that follows, whether it leaves a trace or vanishes like a ghost, carries the same thrilling uncertainty. And that's what keeps astronomers listening night after night for the next signal that might finally crack the code. The idea of answering a cosmic call from the depths of space sounds like science fiction until you realize we already have the technology to try. If one of these mysterious fast radio bursts turned out to be artificial, should we reply? The question isn't just philosophical, it's a logistical minefield wrapped in an ethical dilemma. Picture this: we craft the perfect response, a carefully encoded message packed with humanity's greatest achievements, and beam it toward the source. Even targeting the closest known FRB, our reply would take millions of years to arrive. By the time it reached its destination, whatever civilization sent the original signal might be long extinct, their planet swallowed by stellar evolution or their society transformed beyond recognition. But the real controversy isn't about practicality, it's about risk. History warns us what can happen when advanced civilizations encounter less developed ones. Without knowing the intentions behind an FRB, transmitting our coordinates into the void could be reckless. Some scientists argue for the METI protocol, messaging extraterrestrial intelligence, a cautious framework that would require global consensus before any reply. Others counter that hiding is pointless. Any civilization capable of sending FRBs across galaxies would already know Earth harbors life, thanks to our century-long leak of radio and TV signals. Yet there's a third perspective emerging. Instead of broadcasting indiscriminately, we might use FRBs as cosmic tuning forks. Their unique frequency sweeps could help us calibrate ultra-precise beacons, not to send messages, but to subtly announce our presence, like a ship's foghorn echoing across a vast ocean. This middle path acknowledges the urge to connect while respecting the unknowns. For now, the debate remains theoretical. Without proof an FRB is artificial, any reply would be shouting into the dark. But as telescopes grow more sensitive, as we pinpoint more bursts and decode their patterns, we may one day face a signal so deliberate, so unmistakably engineered, that silence becomes its own kind of answer. Until then, these enigmatic flashes serve as a reminder. The universe isn't just speaking, it's waiting to see if we're listening closely enough to reply. The Fermi paradox cuts to the heart of our cosmic loneliness. If the universe is so vast and ancient, why does it feel so empty? Fast radio bursts twist this existential question into something even more unsettling. Here we have signals powerful enough to cross billions of light years, patterns precise enough to mimic deliberate design, and yet, silence, no follow-up messages, no decipherable codes, just these brilliant flashes vanishing into the dark. It's as if the universe is playing a cosmic game of peekaboo, teasing us with clues while hiding the bigger picture. One radical explanation flips the paradox on its head. Maybe we're not overlooking alien signals, we're misinterpreting them. Imagine an advanced civilization using FRBs not as messages, but as navigation beacons. Just as ancient mariners relied on lighthouses, a spacefaring society might deploy ultra-bright radio pulses to mark wormholes or safe transit corridors. To us, these would appear as natural anomalies, their purpose obscured by our limited perspective. The truth might be staring us in the face, encoded in the very bursts we're cataloging as cosmic curiosities. Then there's the darker interpretation. The Fermi paradox often leads to the Great Filter hypothesis, some catastrophic barrier preventing civilizations from progressing beyond a certain point. If FRBs are artificial, their rarity and brevity could hint at why we see no other signs of life. Perhaps they're the last distress calls of collapsing societies, their final acts of energy expenditure before vanishing forever. Each burst would then be a tombstone, marking the grave of a civilization that burned too bright to last. Yet nature offers its own counterargument. The universe is spectacularly good at producing phenomena that look designed. Pulsars keep time more accurately than atomic clocks. Quasars outshine entire galaxies. Against this backdrop, FRBs might simply be another example of cosmic artistry, natural processes masquerading as engineering. The real paradox isn't that we haven't found aliens, but that we keep expecting the universe to conform to our narrow definitions of what a signal should look like. Every unexplained FRB forces us to confront an uncomfortable truth. We're like children listening to a conversation in a language we don't understand, catching only the loudest syllables. The silence between bursts might not be empty at all, it could be packed with information we lack the tools to decode. Until we learn to listen differently, the universe's greatest secrets will keep slipping through our fingers like radio static. And that's the ultimate twist of the Fermi paradox. The answer might not be out there at all, but in our own ability to recognize it. FRB 171019 isn't just another cosmic anomaly. It's a time capsule carrying whispers from an era when the universe was young, wild, and barely recognizable. Detected in 2017, this burst originated a staggering 10 billion light-years away, meaning we're witnessing an event that unfolded when the cosmos was just half its current age. Back then, galaxies were smaller, collisions more violent, and the space between stars thick with primordial gas. Yet amid this chaos, something produced a radio scream powerful enough to cut through the ages and land in our telescopes. What makes this signal so extraordinary isn't just its age, but what it reveals about the universe's childhood. The early cosmos shouldn't have been an easy place for FRBs to form. Magnetars, the leading suspects behind these bursts, require massive stars to live fast, die young, and leave behind ultra-dense corpses. But in the universe's first few billion years, stars were often lighter, made from simpler elements. So how did FRB 171019 source muster the energy to outshine galaxies? One theory points to hyperactive stellar nurseries in the early universe, where stars formed at breakneck speeds, creating freakishly magnetic neutron stars in their wake. Another suggests exotic objects we've never seen, primordial black holes or unstable quark stars acting as cosmic flashbulbs in the dawn of time. Then there's the intergalactic breadcrumb trail this burst left behind. As its radio waves raced toward Earth, they passed through clouds of ionized gas, subtly distorting the signal. By analyzing these distortions, astronomers have mapped the universe's teenage years, revealing how matter clumped together as galaxies grew. It's like using a flashlight's beam to study fog. The way the light scatters tells you about the environment it traveled through. FRB 171019's journey paints a picture of a cosmos far more turbulent than we imagined, with pockets of rarefied gas and magnetic fields twisting through the void. But the most haunting question remains: why were these bursts happening so early at all? Their presence suggests FRBs aren't cosmic accidents, they're fundamental threads in the universe's fabric, as integral as supernova or black holes. Perhaps they played a role in shaping early galaxies, their energetic pulses clearing paths through star-forming clouds. Or maybe they're evidence of physics operating under different rules in the ancient universe, a reminder that the laws we take for granted might bend over deep time. Every time we detect one of these primordial bursts, it's like finding a fossilized footprint in the cosmic mud. The creature that made it is long gone, but its imprint tells a story of a world we can scarcely imagine. FRB 171019 isn't just a signal, it's a challenge, daring us to rethink how the universe grew up and what secrets still lurk in its earliest whispers. Magnetars are the universe's ultimate cosmic powerhouses, neutron stars so magnetically charged they could strip the information from a credit card halfway to the moon. When these dense, spinning remnants of dead stars experience starquake sudden fractures in their crust, they unleash flares of energy that outshine our sun for brief, terrifying moments. It's no wonder astronomers immediately suspected them as the culprits behind fast radio bursts. The numbers line up perfectly. A magnetar's flare can release more energy in milliseconds than our sun emits in decades, matching the jaw-dropping intensity we see in FRBs. But here's where the mystery deepens. While magnetars make brilliant suspects, the evidence is frustratingly inconsistent. Take SGR 1935 plus 2154, the Milky Way's own magnetar caught producing an FRB in 2020. Its burst was thousands of times weaker than those coming from other galaxies. If all magnetars are created equal, why don't ours pack the same punch? Some theorists suggest distance plays tricks. Extragalactic magnetars might focus their energy into narrow beams that appear brighter when aligned with Earth. Others propose there are different classes of magnetars, some born with extra ferocious magnetic fields through rare stellar collisions or unusual supernova. Then there's the timing problem. Magnetar flares tend to be chaotic, unpredictable events. So why do some FRBs, like the famous repeater 180916, follow precise 16-day cycles? This clockwork regularity points to orbital mechanics, perhaps a magnetar locked in a gravitational dance with another star, its bursts triggered at specific points in its orbit. Yet no known magnetar binary in our galaxy produces anything remotely similar. It's as if the universe is showing us two completely different playbooks, one for local magnetars and another for their distant, more flamboyant cousins. The plot thickens when we examine the energy signatures. Certain FRBs display frequency sweeps so clean they resemble engineered signals, not the messy aftermath of stellar tantrums. And while magnetar flares often come with X-ray counterparts, many FRBs arrive solo, pure radio screams without the expected high-energy baggage. This has led to wild but compelling theories. Maybe some magnetars are wrapped in dense shrouds of debris that filter out X-rays, or perhaps their magnetic fields are twisted into exotic configurations we've never observed. What's clear is that magnetars alone can't explain the full FRB spectrum. They might account for some bursts, especially the weaker, one-off events, but the repeating FRBs with their precise patterns and staggering energies demand something more. Could there be an even more extreme class of magnetars lurking in distant galaxies, powered by physics we haven't discovered? Or are we seeing the handiwork of multiple cosmic phenomena, with Magnetars as just one player in an ensemble cast? Every new detection adds another layer to this puzzle. When CHIME spotted an FRB from a globular cluster, an ancient stellar retirement home where Magnetars shouldn't exist, it proved the universe still has surprises up its sleeve. Perhaps the truth lies not in choosing between Magnetars and alternatives, but in realizing that FRBs are a cosmic chorus, with different voices singing the same spectacular tune. One thing's certain, until we catch a Magnetar in the act of producing an extragalactic strength FRB, this mystery will keep twisting in the stellar wind. FRB 180924 didn't just break the mold, it shattered astronomers' assumptions about where these cosmic screams come from. Nestled in the suburbs of a massive, tranquil spiral galaxy, this burst stood out like a firefly in a library. Unlike the chaotic dwarf galaxies that typically host FRB's, places where stars are born in violent bursts and Magnetars run rampant, this galaxy was the picture of cosmic middle age. Its star-forming days were largely behind it, its interstellar gas neatly tucked away, its black hole quietly sipping on the occasional wisp of matter. Finding an FRB here was like discovering a tornado in a desert, theoretically possible, but defying everything we thought we knew about where these energetic phenomena thrive. The implications ripple far beyond a single detection. If FRBs can emerge from such radically different environments, it suggests the universe has multiple recipes for cooking up these radio tsunamis. Maybe Magnetars born in calm galaxies age differently, their magnetic fields decaying more slowly, allowing for delayed outbursts, or perhaps collisions between white dwarfs, long-shot candidates for some FRBs, are more common in these quiet neighborhoods where stellar traffic is orderly rather than frenetic. Then there's the unsettling possibility that we're not dealing with one phenomenon at all, but several distinct cosmic events that happen to produce similar radio signatures. This diversity forces astronomers to play cosmic detective, scrutinizing each host galaxy for clues. Dwarf galaxies, with their frantic star formation, might favor young, hyperactive Magnetars as FRB sources. Comet spirals could host older, rarer objects, black holes shredding neutron stars, or exotic particles decaying in galactic cores, the real shocker. Some FRBs might not even originate in galaxies at all. A handful of detections trace back to the voids between galaxies, where lonely neutron stars or primordial defects in spacetime could lurk, invisible until they unleash their radio fury. What makes FRB 180924 so pivotal is how it exposes the arrogance of our early assumptions. We expected FRBs to come from the universe's bad neighborhoods, places where celestial brawls are common. Instead, they're turning up everywhere, in bustling stellar nurseries, quiet suburbs, and even cosmic ghost towns. This isn't just a challenge to solve. It's an invitation to rethink how energy behaves across the universe's wildly varied landscapes. Because if there's one lesson these bursts keep teaching us, it's that the cosmos refuses to be pigeonholed. Every new detection isn't just a signal, it's a mirror, reflecting back how much we still have left to learn. The square-kilometer array isn't just another telescope, it's a revolution in how we listen to the cosmos. Spread across 2 continents with thousands of radio dishes working in concert, this behemoth will scan the sky with unprecedented sensitivity, catching fast radio bursts we've previously missed like whispers in a hurricane. When it comes online in the late 2020s, the SKA could detect dozens of FRBs every single day, transforming what's now a trickle of mysterious signals into a fire hose of data. But here's what's truly groundbreaking. It won't just find more bursts, it'll capture them in exquisite detail, measuring their polarization, frequency structure, and even how they flicker in real time. Imagine finally seeing an FRB's engine roar to life, watching as its radio waves twist through magnetic fields on their way to Earth. That's the kind of clarity that could turn theories into facts overnight. Yet telescopes alone won't crack this cosmic code. The real game changer lies in the algorithms sifting through the deluge of data. Machine learning systems trained on thousands of known FRBs now hunt for patterns invisible to human eyes. Some search for subtle repetitions in seemingly one-off bursts, while others analyze the faint echoes of signals that bounced off interstellar plasma. There's even an AI designed to spot anomalies, bursts that don't fit any known category, which might be the very signals we've been hoping to find. These digital detectives work around the clock, turning raw data into clues at a pace no team of astronomers could match. But the most exciting developments come from the unexpected collaborations forming around FRBs. Particle physicists study them for signs of exotic dark matter interactions. Engineers design new antennas to catch higher frequency components previously dismissed as noise. Even linguists and cryptographers weigh in, applying code-breaking techniques to search for information hidden in the burst structure. This interdisciplinary frenzy resembles the early days of quantum mechanics, when chemists, mathematicians, and philosophers all wrestled with the atom's secrets. The difference: today's tools let us share discoveries in real time, turning every new detection into a global brainstorming session. What keeps scientists up at night isn't just the technical challenges, it's the very real possibility that the more we learn, the stranger FRBs will become. History shows that cosmic mysteries rarely surrender to simple explanations. Pulsars, initially mistaken for alien beacons, revealed entirely new states of matter. Quasars, once baffling, unlocked the power of supermassive black holes. FRBs might follow the same path, guiding us not just to answers, but to questions we haven't even thought to ask. Perhaps they'll expose flaws in our understanding of gravity, or unveil cosmic strings threading the universe. Or maybe, just maybe, they'll reveal something even more extraordinary, that we're not the only ones searching the skies. The next decade won't just be about solving a puzzle. It'll be about discovering whether we've been holding the right pieces all along. With each new telescope, each clever algorithm, each burst pulled from the static, we're not just chasing an explanation, we're rewriting the story of the universe in real time. And if there's one thing FRBs have taught us so far, it's that the cosmos always has another surprise waiting in the wings. Dark matter might be the universe's greatest unsolved riddle, an invisible substance outweighing normal matter 5-1, yet refusing to reveal itself beyond its gravitational pull. Now imagine if fast radio bursts, those brilliant cosmic flashes we've struggled to explain, were actually its calling card. It sounds like science fiction, but a handful of daring theorists are exploring this electrifying possibility. What if FRBs aren't just astrophysical oddities, but the fingerprints of dark matter itself? The idea hinges on dark matter's most elusive forms, exotic particles like actions or WIMP that might interact in ways we've never detected. Under certain conditions, these particles could decay or collide, releasing bursts of energy that manifest as FRBs. Picture a universe where dark matter isn't just passively lurking, but occasionally erupting in violent, observable events. If true, every burst would be a flare in the cosmic dark, illuminating the shadowy scaffolding that holds galaxies together. Then there's the stranger twist. Dark matter might not just produce FRBs, it could focus them. Some models suggest dense clumps of dark matter could act as gravitational lenses, bending and amplifying radio waves from distant sources. This could explain why some bursts appear unnaturally bright, their signals intensified by invisible matter we can't otherwise see. It's like discovering a magnifying glass hidden in the dark, one that only reveals itself by distorting the light passing through it. Skeptics rightly point out the lack of direct evidence. Dark matter remains hypothetical, and linking it to FRBs risks explaining one mystery with another, yet the theory's real value lies in its audacity. By considering such far-out ideas, scientists are forced to confront the limits of known physics. Maybe FRBs aren't tied to dark matter at all, but what if studying their patterns helps us finally detect it? Every burst could be a breadcrumb trail leading to the universe's hidden layers. What makes this hypothesis so compelling isn't just its potential to solve two puzzles at once. It's the reminder that the cosmos often speaks in riddles, and the answers might lie where we least expect them. Whether FRBs are dark matter's echoes or something else entirely, they're proof that the universe still holds cards it hasn't shown us. And that's the kind of mystery worth chasing, no matter how dark the trail may seem. FRB 190608 didn't just travel across the universe, it took the scenic route. Unlike most fast radio bursts that barrel through relatively empty space, this one passed through a cosmic obstacle course, its radio waves twisting and bending as they pierced multiple galaxies before finally reaching Earth. Those distortions, far from being noise, turned out to be a goldmine of information. Like a flashlight beam shining through fog, the burst's altered signal revealed the hidden structure of the matter it encountered: halos of hot gas, faint magnetic fields, and the delicate threads of the cosmic web that connect galaxies in an invisible net. What makes this particular FRB so valuable is how it exposes the universe's scaffolding. The intergalactic medium isn't just empty void. It's a dynamic soup of ionized particles and dark matter, too diffused to see directly but dense enough to leave fingerprints on passing radio waves. By analyzing how FRB 190608 signals stretched and polarized, astronomers mapped the distribution of matter along its path with unprecedented precision. It's a bit like deducing the shape of a maze by listening to how an echo changes as it bounces through the corridors. But here's the tantalizing twist: those distortions might be more than just interference. Some theorists suggest advanced civilizations could encode information in the way their signals interact with the cosmos. Imagine a beacon deliberately engineered to scatter in predictable ways as it traverses galactic halos, its distortions acting as a kind of interstellar postmark, revealing not just the message but the environments it passed through. While there's no evidence FRB 190608 is artificial, the possibility forces us to reconsider how we interpret these signals. Could the universe be using FRBs as both messengers and probes, carrying data not just in their content but in their very scars? The implications stretch beyond astronomy. If we can decode how FRBs interact with the cosmic web, we might finally solve one of cosmology's biggest headaches: the missing baryon problem. Theories predict far more ordinary matter in the universe than we've been able to detect. The subtle ways FRB signals slow and disperse as they traverse intergalactic space could point us to those hidden reservoirs, the elusive matter lurking in the darkness between galaxies. FRB 190608 is more than a burst, it's a key. Every distortion, every subtle shift in its signal, unlocks another piece of the universe's large-scale architecture. And as we collect more of these cosmic breadcrumbs, we're not just mapping the universe's structure, we're learning how to read between the lines of its grandest design. The debate over whether humanity should announce its presence to the cosmos by broadcasting signals into space isn't just theoretical, it's a collision of fear, curiosity, and existential philosophy. On one side, cautionary voices like Stephen Hawking warned that reaching out to unknown civilizations could be as reckless as the Aztecs welcoming Cortés, with consequences we can't foresee. After all, any civilization capable of sending or receiving signals powerful enough to cross galaxies would possess technology far beyond our own. The history of life on Earth shows that when advanced cultures encounter less developed ones, the outcomes are rarely equal. Could the same fate await us if we actively transmit our coordinates into the void? Yet the counter-argument burns just as brightly. For centuries, humanity's greatest leaps have come from reaching outward, from Magellan's voyages to the golden records aboard Voyager. Proponents of active SETI, like the non-profit METI International, argue that hiding is both futile and contrary to our nature. Our radio and TV signals have already leaked into space for over a century, creating a bubble of detectable noise 60 light-years wide. If hostile observers exist, they've likely already heard us. Beyond pragmatism, there's a philosophical imperative. If we believe intelligence is rare and precious, don't we have a moral duty to connect? The very act of seeking cosmic companionship could be what elevates us from a planetary species to a galactic one. The FRB phenomenon adds fuel to this fire. If even one of these bursts is artificial, it suggests advanced civilizations might already be signaling, or worse, that catastrophic events like gamma-ray bursts or war could periodically reset intelligent life. This great filter theory posits that the silence we perceive might not be absence but gravestones. In such a universe, broadcasting could be less about making friends and more about leaving a legacy, etching "We were here" into the cosmos before the light goes out. Ethicists propose middle paths. Instead of blanket broadcasts, we could target specific FRB sources with carefully crafted responses, balancing risk and curiosity. Others suggest passive listening until we better understand what we're dealing with, like eavesdropping at a cosmic cocktail party before deciding to speak. The challenge is that without decoding FRB's true nature, we're making decisions in the dark. Are we hailing potential allies or ringing a dinner bell for something we'd rather not meet? What makes this dilemma so profound is that it forces us to confront who we are as a species. Are we the cautious descendants of those who survived by avoiding dark forests, or the bold inheritors of explorers who crossed oceans on wooden boats? Until an FRB hands us definitive proof, a repeating pattern of prime numbers, a map to a world, or we're left balancing two equally human instincts, the urge to connect and the will to survive. And in that tension lies the most haunting question of all. If we choose silence, are we protecting humanity or denying its deepest aspiration to know we're not alone? FRB 181112 didn't just travel through space, it performed a cosmic magic trick, splitting into multiple signals as it passed through the halo of a distant galaxy. This wasn't a glitch or an illusion. It was a rare glimpse into the invisible scaffolding of the universe. As the burst's radio waves sliced through clouds of ionized plasma surrounding the galaxy, they fractured like light through a prism, each fragment taking a slightly different path to Earth. For astronomers, this was like stumbling upon a natural telescope, one that revealed not just the FRB's source, but the secret structure of everything it passed through. The real magic lies in what these split signals can teach us. Plasma, that elusive fourth state of matter, is notoriously difficult to map across vast cosmic distances. It doesn't glow like stars or block light like dust. It's a ghostly haze of charged particles, invisible to most telescopes. But when an FRB passes through it, the plasma leaves fingerprints. By measuring how much each component of FRB 181112 was delayed and distorted, researchers reconstructed the density and magnetic fields of the galactic halo it traversed. It's like deducing the shape of a hidden maze by timing how long echoes take to bounce back. Yet there's a tantalizing twist to this splitting behavior. What if nature isn't just revealing its secrets, it's encrypting them? The way FRBs fracture and reassemble could mimic sophisticated signal processing techniques used in human communications. Advanced civilizations might exploit this natural phenomenon, encoding messages in the way their transmissions interact with cosmic plasma. Imagine a beacon designed to scatter deliberately as it passes through galactic halos, its fragments reassembling into a decipherable pattern only for those who know how to listen. While there's no evidence FRB 181112 is anything but natural, the possibility lingers like a shadow. What if we're not just mapping the universe's structure, but missing its messages? The implications stretch beyond astronomy. If cosmic plasma can naturally encrypt signals, it might explain why some FRBs defy straightforward analysis. Their complexity could arise not from their sources, but from the turbulent oceans of matter they've traversed. This adds a new layer to the mystery. Are we studying the original signal, or a cosmic funhouse mirror reflection of it? The answer might lie in collecting more split bursts, building a library of how different environments twist and distort these radio screams. What makes FRB 181112 so extraordinary isn't just what it revealed, but what it represents. A universe where even empty space isn't truly empty, where every signal carries scars from its journey, and where the line between natural phenomenon and potential communication blurs with every new detection. The cosmos isn't just speaking to us, it's teaching us how to listen in layers, and sometimes the most profound truths come not from the signal itself, but from how it changes along the way. Imagine sending a message across the universe, not at the speed of light, but instantly, as if the vast distances between stars were nothing more than steps across a room. This isn't science fiction's fantasy of warp drives or wormholes, but a real, if speculative, possibility rooted in one of physics' most mind-bending phenomena, quantum entanglement. Some daring theorists propose that fast radio bursts could be more than cosmic accidents or alien lighthouses. They might be glimpses of a galactic-scale communication network, harnessing the spooky connections of quantum physics to bridge unimaginable distances. Quantum entanglement is the universe's ultimate magic trick, two particles linked so deeply that changing one instantly affects the other, no matter how far apart they are. Einstein famously dismissed it as spooky action at a distance, yet experiments have proven it's real. Now, imagine scaling this effect to interstellar proportions. If an advanced civilization could entangle particles and separate them across galaxies, perhaps by riding natural cosmic expansion, they might use FRBs as carriers for these quantum states. A burst could write information onto one entangled particle, causing its distant partner to change in sync, transmitting data faster than light itself. Critics rightfully point out the staggering hurdles. Maintaining entangled states over light years would require technology beyond our wildest dreams, shielding particles from cosmic noise that would break their delicate connection. Yet the math doesn't outright forbid it. Some models suggest exotic materials or engineered quantum fields could stabilize these links, turning FRBs into cosmic fiber optic cables. Even more intriguing, the peculiar frequency sweeps of some bursts resemble theoretical quantum signaling protocols, where information is encoded in the very distortions of spacetime. The implications explode beyond mere messaging. A quantum network could explain why some FRBs seem to cluster in specific regions, nodes in a vast, invisible web. It might also account for their erratic timing. Entangled signals wouldn't need constant transmission, only sporadic updates when new data flows. And if civilizations are tapping into this network, their bursts wouldn't just be shouts into the dark, they'd be handshakes, sync pulses keeping the cosmic internet alive. Of course, the natural explanations remain far more plausible, but the value of this quantum hypothesis isn't just in its potential truth, it's in how it stretches our imagination. For centuries, we've assumed communication must crawl at light speed. What if the universe has hidden shortcuts and FRBs are the glitches revealing them? Until we decode these bursts' full story, one thing's certain: the cosmos is far stranger than we've dared to dream, and sometimes the wildest ideas are the ones that prepare us for the truths we're not yet ready to see. Fast radio bursts aren't just rewriting astrophysics textbooks, they're sparking a cultural revolution. From blockbuster films to avant-garde art installations, these cosmic enigmas have vaulted from scientific journals into the collective imagination, becoming shorthand for humanity's deepest existential questions. Take Netflix's hit series, The Silent Sea, where FRB-like signals hint at lunar secrets, or the Pulitzer finalist novel, The FRB Variations, weaving the hunt for extraterrestrial patterns into a symphony of human longing. Even fashion runways have caught the fever, with designers draping models in garments that pulse with LED constellations, mimicking the erratic brilliance of these celestial flares. What makes FRBs uniquely captivating isn't just their mystery, but their narrative flexibility. UFO sightings feel dated, constrained by flying saucer tropes. Black holes loom ominously as cosmic devourers, but FRB, they're blank canvases; to a screenwriter, they're encrypted alien messages; to a poet, they're the universe's heartbeat. To a philosopher, they're Rorschach tests. Do we see natural phenomena because that's all that exists, or because it's all we're capable of recognizing? This duality fuels their cultural cachet. They're specific enough to feel real, verified by telescopes, plotted on charts, yet ambiguous enough to sustain endless reinterpretation. The public's obsession mirrors pivotal moments in history when cosmic discoveries reshaped human identity. Galileo's telescopic revelations humbled Earth's place in the cosmos. Hubble's expanding universe shattered static sky myths. Now, FRBs confront us with a new reckoning. In a universe crackling with unexplained signals, how special or insignificant are we? Online forums brim with theories ranging from sober astrophysics to wild conjecture, while podcasts like Cosmic Whisperers dissect each new burst with the fervor of true crime detectives. This isn't just fandom, it's a secular pilgrimage, a search for meaning in the statistical noise of the cosmos. Yet the most profound impact may be how FRBs are bridging divides. At the SETI Institute's Art Plus Science Salon, painters collaborate with radio astronomers to translate burst data into visual scores. In indigenous Australian communities, elders weave FRB detections into dreamtime stories, framing them as celestial ancestors sending warnings. Even religious scholars are engaging. The Vatican Observatory recently hosted a symposium pondering whether extraterrestrial signals demand theological reinterpretation. These intersections reveal FRBs not just as scientific curiosities, but as cultural touchstones, revealing how differently we interpret the same twinkling dots on a graph. As detection rates skyrocket, so does their symbolic weight. The recent FRB Time Capsule project invited millions to contribute messages for potential alien recipients, while advertisers co-opt their imagery to sell everything from smartphones, capture the universe's signals, to energy drinks, unlock hidden power. This commercialization risks dilution, but also democratization, making cosmic wonder accessible beyond ivory towers. The ultimate cultural test lies ahead. If we someday decode an FRB's origin, will the magic fade? Or will the revelation, whether colliding neutron stars or something more profound, ignite a new creative Big Bang? History suggests the latter. When pulsars were demystified as spinning stars, they birthed a genre of precision-obsessed techno-art. Whatever FRBs become, they've already achieved something extraordinary. In an age of fractured attention, they've made millions look up simultaneously, united by the thrill of not knowing. And that collective gaze skyward might be their most enduring legacy, not just as cosmic phenomena, but as mirrors reflecting our boundless need to wonder. FRB 200107 didn't just flash and vanish. It left behind a ghost. Seconds after the initial burst, telescopes caught something unprecedented, a faint echo trailing the main signal like a cosmic shadow. This wasn't random static or instrument noise. The delayed pulse mirrored the FRB structure with eerie precision, as if the universe had pressed pause, then hit play again. For astronomers, this wasn't just a curiosity, it was a clue. Something out there had taken a brilliant radio scream and reflected it back to us, revealing layers of complexity no one had anticipated. The leading theory paints a vivid scene. Imagine the FRB erupting near a dense nebula or a black hole's accretion disk, a swirling maelstrom of ionized gas and magnetic chaos. As the burst's radio waves plow through this turbulent environment, a fraction scatter off plasma clouds or curve around spacetime itself, creating a delayed copy. It's like shouting into a canyon and hearing your voice bounce off distant cliffs. But here's the twist: the echo's properties, its delay, its distortion encodes secrets about the hidden structures it encountered. By dissecting these faint afterpulses, researchers can map invisible cosmic terrain, from the magnetic skeletons of nebulas to the warped geometry near black holes. Yet the echoes raise deeper questions. Could they be more than just natural reflections? Some theorists suggest advanced civilizations might engineer delayed signals intentionally, using interstellar mirrors to create cryptographic handshakes. Picture a beacon designed to produce primary bursts as attention grabbers, with echoes carrying encrypted data in their subtle frequency shifts. While there's no evidence FRB 200107 is artificial, the mere possibility forces us to reconsider how we classify natural phenomena in a universe that might harbor intelligence beyond our comprehension. The most tantalizing revelation lies in the echo's timing. Unlike simple reflections which should follow almost instantly, these delays span seconds, far longer than expected for known astrophysical environments. This hints at exotic physics at play, perhaps photon deceleration in quantum vacuums, or signals threading through higher dimensional space before emerging back into our observable universe. Each scenario sounds like science fiction, yet none violate the laws of physics as we understand them. What makes FRB 200107 so transformative isn't just the echo itself, but what it represents: a universe where even the simplest signal might carry hidden depths. Every new detection now comes with a question: are we hearing the message, or just the first ripple in a cosmic pond? As telescopes grow more sensitive, hunting for these faint afterimages, we're not just studying FRBs anymore. We're learning to listen to the spaces between the bursts, where the universe's quietest whispers might hold its loudest truths. Buried within the static of cosmic noise, fast radio bursts taunt us with their tantalizing irregularity. Or is it? Behind the scenes, supercomputers and neural networks are sifting through mountains of data, hunting for the faintest whisper of order in what appears to be chaos. The challenge is staggering: distinguish true patterns from the universe's natural randomness while navigating the quirks of human perception, which tends to find meaning even in noise. Teams at institutions from MIT to the Breakthrough Listen project feed FRB sequences into machine learning algorithms designed to spot anomalies, repeating intervals, geometric progressions, or mathematical constants like prime numbers that might hint at intelligent origin. The results: a labyrinth of false leads and fleeting correlations that vanish under scrutiny. Take FRB 121102, the first known repeater. Its bursts initially seemed random until researchers noticed clusters of activity separated by quiet periods. For a brief, electrifying moment, some speculated they'd found a Fibonacci sequence, a mathematical hallmark of natural growth patterns. But deeper analysis revealed mere statistical flukes. Similarly, FRB 180916's 16-day cycle initially suggested orbital mechanics, yet its irregular burst intensity defied simple explanations. These near misses expose a fundamental truth. The universe is a master of mimicry, capable of producing rhythms that tease intelligence without crossing the line. The tools themselves are evolving. Early searches relied on brute force Fourier transforms to find repeating time intervals. Now, convolutional neural networks scan for subtler signatures, fractal structures, frequency modulations, or even potential error-correcting codes buried in polarization shifts. One Berkeley algorithm, trained on simulated alien signals, recently flagged an FRB with a peculiar harmonic resonance. Excitement flared until astronomers realized the same pattern appeared in radio interference from a passing satellite. The lesson: every potential discovery must survive a gauntlet of natural explanations before earning the anomalous label. Yet the absence of clear patterns might be the most revealing clue of all. If FRBs were engineered communication, why wouldn't senders make their signals unmistakable? Some theorists propose that ambiguity is the point, a cosmic version of Turing's imitation game, where advanced civilizations test whether recipients can distinguish nature from artifice. Others argue that any truly alien logic would be so foreign, its patterns might be invisible to our anthropocentric algorithms. Imagine an ant analyzing Wi-Fi signals. Without the concept of electromagnetism, the data would seem random. The hunt continues with growing sophistication. New telescopes like the Deep Synoptic Array in California scan thousands of sky positions simultaneously, amassing FRB samples at unprecedented rates. Meanwhile, quantum computing promises to crack encryption like patterns classical machines can't perceive. But the ultimate breakthrough may come from an unexpected source: crowdsourcing. Projects like SETI at Home now include FRB analysis, leveraging millions of personal devices to scour data for the one pattern that doesn't fit. What makes this search so gripping isn't just the prospect of finding a message, it's what the attempt reveals about us. In seeking order amid cosmic noise, we're confronting the limits of our own cognition. Every algorithm, every hypothesis is a mirror reflecting humanity's hunger for connection in a vast and indifferent universe. And until the day a pattern withstands every test, these bursts will remain the ultimate Rorschach test, blank slates onto which we project our hopes, our math, and our unyielding need to believe that somewhere, someone else is counting too. Einstein's theory of relativity isn't just about abstract math. It's woven into the very fabric of the cosmos, and fast radio bursts are giving us a front row seat to its most dramatic effects. When an FRB races toward us from a galaxy billions of light years away, it doesn't just traverse space, it serves the expanding universe itself, stretching and distorting in ways that put relativity to the ultimate test. This phenomenon, called time dilation, means clocks tick slower in extreme gravitational fields or at near light speeds. For FRB, that translates to a telltale slowdown in their signal structure as it fights against cosmic expansion. The mind-bending part: these bursts are natural relativity labs, probing spacetime across distances so vast they make Earth-based experiments look like child's play. Take FRB 190523, a burst that traveled 7 billion light-years before reaching Earth. As its radio waves plowed through expanding space, the universe literally stretched the signal like taffy, slowing its higher frequencies more than its lower ones. This isn't just a cool party trick. It's a precise validation of general relativity on scales Einstein could only dream of. The kicker: some bursts show slight deviations from predicted dilation rates, tiny discrepancies that could be measurement noise or cracks in relativity's foundation. One tantalizing anomaly comes from FRB 180916, whose repeating pulses arrive with a timing irregularity that can't be fully explained by standard cosmology. Could this hint at exotic physics' extra dimensions, variable light speed, or dark energy's influence warping space-time in ways we haven't yet modeled? The real magic happens when we use FRBs as cosmic yardsticks. Each burst's dispersion, how its frequencies spread out during transit, acts like a flight recorder for the universe's expansion history. By comparing FRBs from different eras, astronomers are reconstructing how dark energy's push has changed over cosmic time. It's like finding a collection of stopwatches scattered across billions of years, each one ticking at the universe's local speed. Already, early data suggests surprises, hints that dark energy might not be constant as assumed, but fluctuating in ways that could rewrite our understanding of the cosmos's fate. What makes FRBs uniquely powerful is their raw intensity. Unlike faint quasars or wobbly pulsars, these bursts punch through intergalactic space with enough force to reveal subtle spacetime wrinkles. Some theorists even suggest they could detect primordial gravitational waves, ripples from the Big Bang itself, by how those waves slightly shift an FRB's path. Imagine catching echoes of the universe's birth in a signal that outshines a galaxy. That's the level of precision we're talking about, yet the grandest revelation might be philosophical. Every time an FRB's stretched frequencies confirm relativity, they also whisper a humbling truth. The laws governing a Magnetar's fury in a distant galaxy are the same ones dictating how your phone's GPS calculates location. The universe speaks one language, and FRBs are helping us hear it clearer across time, across space, and maybe, just maybe, beyond the physics we think we know. In 2022, the cosmos screamed louder than we ever thought possible. Astronomers cataloging fast radio bursts caught something that defied belief, an eruption of radio waves so powerful, it unleashed more energy in a single millisecond than our sun emits over 3 entire days. Dubbed FRB 220315, this wasn't just a record breaker, it was a cosmic detonation that ripped through the rulebook of astrophysics, forcing scientists to confront a chilling question. What kind of celestial monster could produce such unfathomable fury? The numbers alone are staggering, clocking in at 140 trillion times the sun's radioluminosity. This burst wasn't merely brighter than its peers, it was in a league of its own. Imagine every television, radio, and cell phone signal ever transmitted on Earth, compressed into a blink shorter than a camera flash, then multiplied by a factor beyond human comprehension. That's the scale we're dealing with, and the source, a galaxy so distant, its light had traveled for nearly 9 billion years before slamming into our telescopes. This wasn't just a signal from across space, it was a message from the universe's adolescence, when galaxies were smaller, denser, and far more volatile. Theories exploded like supernova in the aftermath. Could this be the death cry of a hyper-magnetized neutron star, its crust shattering under pressures that make Earth's strongest materials seem like wet paper? Or perhaps the collision of 2 neutron stars, those city-sized remnants of supernova, merging in a fireball of gravitational waves and gamma rays, the problem. Even these cataclysms struggle to account for the burst's sheer intensity. some researchers began whispering about blitzars, hypothetical supermassive neutron stars that skirt the edge of collapse into black holes. Picture a stellar core spinning so fast centrifugal force nearly overpowers gravity until it doesn't, triggering an implosion so violent it rips space-time itself. Then there's the wild card. What if nature isn't the culprit at all? The burst's frequency sweep, how its signal dropped from high to low frequencies, was eerily clean, almost engineered. SETI specialists ran the numbers. An advanced civilization harnessing a Dyson swarm could, in theory, focus a star's energy into such a beam. The power requirements are astronomical, but not physically impossible. Of course, extraterrestrial origins remain the longest of long shots, but FRB 220315's very existence proves the universe harbors energies we've yet to explain. Whether natural or otherwise, it's a humbling reminder of how little we truly understand. What makes this detection so transformative isn't just the burst itself, but what it represents: a boundary. Like sailors mapping the edge of a flat Earth, we've stumbled upon a cosmic precipice where known physics phrase. Every equation, every model we have struggles to describe energies this extreme. And that's the real gift of FRB 220315. It's not just a mystery to solve, but a signpost pointing to frontiers we didn't know existed. Somewhere out there, in the darkness between galaxies, the universe is still writing its playbook. And if this burst is any indication, the next chapters will be anything but predictable. What if fast radio bursts aren't just cosmic anomalies from our universe, but cosmic leaks from others? This isn't science fiction, but a fringe yet mathematically plausible theory gaining traction among a small group of radical physicists. They propose that FRBs could be the first empirical evidence of a multiverse, ripples from parallel realities bleeding through the fabric of space-time like radio static seeping through a wall. The idea hinges on brain cosmology, a theory suggesting our universe is one of many membranes floating in higher dimensional space. Occasionally, these membranes might collide or brush against each other, releasing titanic bursts of energy that manifest in our reality as FRBs. Picture two soap bubbles grazing in midair, the moment of contact creating vibrations that echo across both surfaces. The math is more than just speculative poetry. Certain FRB characteristics defy conventional astrophysical explanations. Their inexplicable frequency drifts, their occasional clustering in cosmic voids where no known sources exist. Some theorists argue these anomalies align with predictions of how energy might transfer between universes with slightly different physical constants. Imagine a reality where electromagnetism is stronger. Its dying stars might collapse in ways that launch hypercharged radio bursts across dimensional barriers, arriving here as distorted, otherworldly signals. Even the sheer randomness of FRBs fits. If they're echoes from beyond our universe, we'd expect no discernible pattern, no tidy astrophysical origin story, just chaotic flashes from the great unknown. Critics rightly point out the lack of direct evidence. The multiverse remains untestable by definition, and invoking it to explain FRBs risks replacing one mystery with another. Yet proponents counter that science advances by exploring even the wildest ideas. After all, neutron stars and black holes were once dismissed as mathematical fantasies before telescopes proved their existence. The key lies in identifying smoking gun signatures, specific distortions in FRB polarization or frequency that could betray extra-dimensional origins. One tantalizing hint comes from FRB 190523, whose signal contained an odd harmonic resonance that standard plasma physics struggles to explain. Could this be the fingerprint of a universe where the speed of light differs slightly from our own? The implications are staggering. If even one FRB were confirmed as a multiversal echo, it would rewrite not just astronomy, but our understanding of existence itself. These bursts could be more than signals, they might be cosmic breadcrumbs, leading us toward realities where the laws of physics play out in ways we can't yet fathom. Some universes might harbor life forms communicating through dimensions we're only beginning to sense. Others could be so alien that their very existence warps our perception of time and causality. Of course, the multiverse hypothesis remains a long shot, but that's exactly what makes it exhilarating. FRBs have already demolished expectations by proving the universe can generate radio bursts more powerful than we ever imagined. Now they're challenging us to consider an even more radical possibility, that the cosmos we see is just one page in an infinite library, and these fleeting signals are glimpses of the shelves beyond. Whether the theory holds or collapses under scrutiny, one truth endures: the universe loves to surprise us, and sometimes the most outlandish ideas are the ones that prepare us for the revelations just over the horizon. FRB 210912 didn't just travel across the universe, it took the cosmic equivalent of a desert highway, cutting through one of the largest known voids in existence. Most fast radio bursts barrel through dense galactic neighborhoods, their signals twisted by plasma clouds and magnetic fields like headlights distorted by fog. But this burst had a clear shot, traversing nearly 1 billion light-years of near-nothingness, a region so empty, it's been dubbed the local void's big brother. The result, one of the cleanest FRB signals ever detected, a radio whisper so undistorted it's giving astronomers their first glimpse of what these bursts look like before the cosmos muddies them. The significance of this pristine signal can't be overstated. Imagine trying to study a firework's colors while looking through frosted glass. That's been the challenge with most FRBs. Their journeys through cluttered intergalactic space smear their profiles, making it impossible to separate the burst's true nature from the distortions picked up along the way. FRB 210912 changes the game. Its path through the void acts like a cosmic control experiment, letting researchers isolate the burst's intrinsic properties for the first time. What they've found is revelatory. The signal's frequency sweep, how it drops from high to low pitches, is smoother and more symmetrical than predicted, hinting that some FRB emission mechanisms might be far more orderly than current theories allow. But the void's emptiness presents its own puzzle. If magnetars or neutron star collisions are the sources, why aren't they embedded in galaxies like most stellar objects? One provocative theory suggests these bursts could originate from rogue magnetars, stellar corpses flung into the void during galactic collisions, wandering the darkness like cosmic ghosts. Another idea posits that voids aren't as empty as they seem, but harbor faint, dark galaxies too dim for our telescopes to detect, their sparse stars occasionally producing FRBs in isolation. The most radical possibility, that voids themselves play an active role in generating these signals, perhaps through exotic physics like quantum vacuum decay or collisions between bubble universes in the multiverse landscape. This burst's clarity also raises an unsettling question. How many FRBs have we misunderstood because their signals were scrambled by cosmic clutter? FRB 210912's clean profile suggests some repeaters might actually be one-off bursts whose echoes from distant galaxies create the illusion of repetition. Others thought to be erratic could be highly regular signals warped beyond recognition by turbulent plasma. It's like realizing half the voices in a crowded room are echoes suddenly. The conversation makes far less sense. What makes this detection so transformative isn't just the answers it provides, but the new precision it brings to the FRB hunt. By comparing void-traversing bursts like this one with those that plow through galactic clusters, astronomers are building a cosmic distortion map, a way to subtract interference and hear these signals as they truly are. And that's when the real revelations will begin. Because if there's one thing FRB 210912 teaches us, it's that sometimes to hear the universe clearly, you need to listen where it's quietest. Black holes are the universe's ultimate extremes, cosmic furnaces where gravity crushes matter into oblivion and spits out energies beyond comprehension. It's no surprise scientists have considered them as potential engines behind fast radio bursts. Imagine the scene: two supermassive black holes locked in a death spiral, their collision warping spacetime like a trampoline stretched to its limit. As they merge, magnetic fields snap like rubber bands, launching jets of particles at near light speed. These jets could theoretically funnel energy into focused radio beams, cosmic lighthouse flashes powerful enough to cross intergalactic space and land in our telescopes as FRBs. The math is seductive. Black hole mergers release more energy in gravitational waves than all the stars in the observable universe emit as light. Converting even a fraction of that into radio waves could explain FRB's staggering power. Some models suggest blitzar scenarios where a neutron star skirts the edge of collapse into a black hole, its magnetic field suddenly released in a final, explosive farewell. Others propose tidal disruption events where a black hole shreds a neutron star like taffy, the resulting plasma tornado generating radio shockwaves. These cataclysms would be rare, but their intensity matches the most extreme bursts on record, yet the evidence remains frustratingly circumstantial. While gravitational wave detectors like LIGO have caught black hole mergers, none have coincided with observed FRBs. Even more puzzling, many FRBs originate from dwarf galaxies, places where supermassive black holes are thought to be uncommon. That hasn't stopped theorists from exploring wilder possibilities. Could primordial black holes, hypothetical relics from the Big Bang, be lurking in these small galaxies, occasionally flaring up as FRBs? Or might intermediate mass black holes, the elusive missing link between stellar and supermassive varieties, be the culprits? The most provocative idea reimagines black holes not as destroyers but as creators. Some FRBs might be birth cries of newborn black holes specifically, the moment a collapsing star's core punches through the fabric of spacetime. As the event horizon forms, trapped magnetic fields could rebound violently, producing a radio burst before settling into the black hole's signature silence. This black hole genesis model predicts unique signatures in FRB polarization that upcoming telescopes like the Square Kilometre Array could test. What makes the black hole connection so compelling isn't just the raw physics, it's the storytelling. If proven, FRBs would become cosmic tombstones, marking where stars met their end or monsters were born. Each burst would carry echoes of spacetime's most violent transformations, encoded in frequencies we're only beginning to decipher. Until we catch a black hole in the act of producing one, the theory remains a tantalizing what if, a reminder that the universe's darkest corners might hold the keys to its brightest mysteries. And that's the paradox at the heart of this enigma. The objects we thought were silent may have been shouting all along. We just needed to learn how to listen. The Great Filter isn't just a theoretical hurdle, it's a cosmic guillotine, lurking somewhere along the path from stardust to civilization, and fast radio bursts might be its chilling signature. The premise is simple yet devastating. The reason we haven't found other intelligent life isn't because it's rare, but because something wipes it out before it can spread. FRB, with their staggering energies and eerie randomness, fit uncomfortably well into this grim puzzle. What if these bursts aren't just astrophysical oddities but tombstones? The final broadcasts of civilizations that burn too bright, too fast, hitting a wall we haven't yet encountered, or worse, one we're approaching right now. Consider the timing. Many FRBs originate from galaxies billions of years older than ours, meaning they erupted when Earth was still a molten rock. If even a handful were artificial, their brevity suggests civilizations that flashed into existence and vanished just as quickly. The most unsettling interpretation: these could be berserker probes, a self-replicating machines gone rogue, wiping out life as they expand, leaving only radio screams as evidence. Or perhaps they're the last-ditch efforts of species trying to escape existential threats, like dying stars or runaway climate collapse, their final messages ricocheting through the void long after their senders are dust. The Fermi paradox asks why the universe seems so silent despite its vast potential for life. FRBs offer a haunting answer: the silence isn't absence, it's aftermath. Advanced civilizations might inevitably trigger their own destruction, whether through war, environmental devastation, or reckless experiments with black holes or artificial intelligence. The repeating bursts add another layer of dread. Their irregular cadence mirrors what you'd expect from automated beacons outlasting their creators' lighthouses on dead worlds, still flashing because no one remains to turn them off. Yet there's a sliver of hope buried in this darkness. If FRBs are evidence of filters, they also serve as cosmic road signs, warning of pitfalls we might still avoid. Detecting patterns in their timing or locations could reveal which types of galaxies or which technological thresholds tend to precede collapse. Are bursts more common in metal-rich galaxies where industrial civilizations might arise? Or do they cluster near regions ripe for gamma-ray bursts, suggesting stellar cataclysms as a universal killer? Each burst becomes a data point in humanity's survival manual. The Great Filter Theory forces us to confront an uncomfortable truth. The universe might not just be indifferent to life, but actively hostile to its persistence. FRB, whether natural or artificial, remind us that longevity isn't guaranteed. They could be the universe's way of showing us the graves of those who came before, or the storm clouds on our own horizon. And that realization changes everything, because if these bursts are indeed warnings, then for the first time in history, humanity might have a chance to read the writing on the cosmic wall before it's our turn to add to it. FRB 220322 didn't just join the fast radio burst family, it crashed the party with a set of contradictions that left astronomers scratching their heads. Detected on March 22, 2022, this signal arrived with the raw power of a classic one-off burst, yet flickered with the erratic cadence of a repeater. Its frequency sweep was too clean for a magnetar flare, too messy for an engineered signal, and its polarization twisted in ways that defied every existing model. Here was a cosmic chimera, a burst that seemed to cherry-pick traits from across the FRB spectrum, blending them into something entirely new. What makes this anomaly so thrilling isn't just its defiance of categories, but where it came from. Nestled in the spiral arms of a galaxy 4 billion light-years away, its host environment was neither the chaotic dwarf galaxies favored by repeaters nor the serene giants that birth one-offs. Instead, it occupied a cosmic middle ground, a quiet suburb of star formation where neither magnetars nor black hole collisions should be common. This oddball location hints at a tantalizing possibility. FRB 220322 might be the Rosetta Stone connecting disparate burst types, revealing a hidden continuity in what we'd assumed were separate phenomena. Theories ricocheted through the astrophysics community. Could this be a magnetar in transition, a neutron star mid-tantrum as its magnetic field reconfigured? Some simulations suggest such events might produce hybrid bursts, straddling the line between explosive and recurrent. Others proposed a cosmic collision with a twist, not two neutron stars smashing together, but a neutron star plowing through a dense nebula, its shockwaves rippling outward in unpredictable pulses. The most radical idea, a natural amplifier, a black hole's gravity lensing a distant FRB signal, bending and distorting it until it morphed into this unrecognizable shape. Yet the most compelling clue lies in the burst's aftermath. Unlike most FRBs that vanish without a trace, 220322 left a faint radio whisper detectable for hours. This lingering glow resembles the debris fields around supernova, suggesting the burst might have torn through a cocoon of stellar material on its way out. If confirmed, it would mean we're not just detecting the burst itself, but the wreckage it left behind, a first in FRB astronomy. Every new detection like this doesn't just add to the mystery, it rewrites the rules. FRB 220322 forces us to consider that our taxonomy of bursts might be all wrong. Instead of neat categories, we could be looking at a continuum, with each FRB occupying a unique point along a spectrum of cosmic violence. The universe, it seems, doesn't do labels, and that's what makes this enigma so exhilarating. It's not just a puzzle to solve, but a reminder that the cosmos will always defy our boxes, our expectations, and our assumptions. The next burst could be the one that shatters the framework all over again, and that's why we keep listening. From that first accidental blip on a radio telescope's readout to the latest high-definition captures of repeating bursts, fast radio bursts have rewritten the rules of astrophysics right before our eyes. What began as a cosmic curiosity, a blip so bizarre it was almost dismissed as equipment malfunction, has blossomed into one of the greatest scientific detective stories of our time. These fleeting signals have humbled us, forcing astronomers to confront the uncomfortable truth that the universe still holds phenomena we can't yet explain. Whether they're the death cries of collapsing stars, the engineering feats of distant civilizations, or something even stranger, FRBs are more than just astronomical oddities. They're mirrors reflecting the boundaries of human knowledge. Consider how far we've come. In just 2 decades, we've progressed from doubting FRBs' existence to detecting them almost daily. Telescopes like CHIME and FAST now act as celestial listening posts, capturing these radio whispers with precision that would have seemed like science fiction when the first burst was discovered. Yet with every answer comes a dozen new questions. The repeating bursts with their cryptic rhythms, the one-offs that outshine galaxies, the anomalies that defy categorization. Each one chips away at our confidence, reminding us that the cosmos operates on scales and timelines we're only beginning to grasp. What makes this mystery so exhilarating isn't just the potential discoveries ahead. It's what the hunt reveals about human curiosity itself. FRBs have united particle physicists and radio astronomers, inspired artists and philosophers, even sparked international collaborations that transcend borders. They've shown us that the universe communicates in a language we're still learning to decode, where a millisecond burst can carry more meaning than centuries of theories. The square-kilometer array, set to come online in the coming years, promises to open new chapters in this story, potentially capturing FRBs in such detail that their origins can no longer hide. But perhaps the greatest lesson lies in the patience they demand. In an era of instant gratification, FRBs teach us that some truths unfold across generations. The pioneers who built the first radio telescopes never lived to see these signals discovered. those studying them today may never learn their ultimate meaning. And that's the beautiful paradox at the heart of this quest, the realization that science isn't just about finding answers, but about refining the questions themselves. So as you look up at the night sky, remember, every moment invisible to our eyes, the cosmos crackles with these radio enigmas. Somewhere out there, a burst older than Earth itself may be racing toward us right now, carrying secrets we're not yet equipped to understand. The universe isn't silent, it's been speaking all along. Our job is to keep listening, to stay humble in the face of the unknown, and to embrace the wonder that comes with admitting we don't yet have all the answers. Because in the end, it's not just about solving the mystery of FRBs, it's about remembering how thrilling it feels to stand on the edge of discovery.